Hi guys, I'm going to max this guy out for a sec. Now, I'm going to start over from where I started. We ended up last time, so I'm going to go over that once again. So we're going to do, last class we were talking about hash table of size 2. P of 0 is the probability of hashing to 0. P of 1 is probability of hashing to 1, since the two items in the table 0 and 1. P of failure is the probability of the searched item actually not in the hash table. I don't know why it says in the hash table. That's a typo. Okay. So, now you'll remember from linked list, the probability is 1 minus the P of failure, that's the P of success, times n plus 1 over 2. Now, in this case, okay, so P of 0 time, we're in the 0 thing, and we're going to go n. The length of the list is n P of 0, since of the n items, P of 0%, like if it was in half of the n items would end up in this part. If it's if 1/3 of the guys go to 0, 1/3 of n will end up. So the length of the list is going to be on average n P of 0 plus 1 over 2, plus the probability of failure times n P of 0. Once again, the length of the list in P of 0 on average, plus 1 minus P of 0, that's P of 1, probability of 1, times 1 minus, once again the same math, but with 1 minus P of 0. So here, this is the length of the list in position 0. This is the length of the list at position 1. And this, too, is the length of the list at position 1. So this is the same math from searching a linked list. We're assuming that the linked lists in our hash table are unsorted, because almost always they are. Okay, the whole point is we're not going to gain by sorting, we're going to gain by building a sufficiently large hash table. Now we're doing a small one now, size 2. Okay, so now I'm going to do a bunch of algebra on this. So I repeat this formula. This is where, so that was just a review. I'm going to repeat the formula now and do some combining of like terms and stuff. So first thing I'm going to do is take these terms and move them into the fraction by making this is 2 times P of failure n P of 0 over 2. So this goes into the same fraction. And I do the same thing right over here, so this becomes 2 over 2, you see. And this guy does the same thing. From P of failure up here, this guy, it becomes 2 P of failure over 2. So that just gives me 2 fractions here. Let's squeeze that a little bit again so things appear onto one. That's too small. Okay. Now, we're going to what I did is I start doing some like term combining. So first, I do some distributing first. So I take 1, you see this 1 minus P of failure over here, and I take this n P of 0 plus 1, and I multiply by 1, and I subtract P of failure. So I distribute that guy. So far, nothing very interesting is happening, but that's okay. And I do the same thing with taking this guy and distributing it to 1 minus P of failure over here. Okay? Now, then I do some combining of like terms. Well, do I do that yet? The first thing I do is distribute P of failure into this guy and distribute P of failure into that guy. Okay, I'm trying. Then, okay, so this guy, all I'm doing is taking this P of failure times this guy and distributing it to give me this formula. And I do the same thing over here. I take this P of failure over here and distribute it into its guy over there. That gives me this guy. Now I can combine like terms. Okay, so what's going to happen is this, there's two P of failures and, okay, so let's start here. There's two P of failures and P of 0 minus one P of failure and P of 0. So this guy gets subtracted from this guy, and it's going to give me a 1 P of failure and P of 0. Okay. Now, so that's what that plus comes from. And then this guy is just subtracting a P of failure. Okay. Now, so what also is happening is okay, let me see. Oh, here. Okay, so I'm up here. Okay, so I have these two P of failures minus a P of failure, and the other thing is, oh, I didn't do anything. I just did NP of 0 minus plus 1. I took out the parentheses because they're not doing anything for me. And this is the same thing, except this one I had the 2 P of failure n times 1 minus P of 0 minus 1 P of failure n times 1 minus, and everything else is still the same. Now, at this point, I distribute this guy, P of 0, and this guy, 1 minus P of 0, into these and make it one big fraction over 2. So this P of 0 times NP of 0, silly thing, turns into NP of 0 squared. 1 times P of 0 becomes P of 0. This NP of 0 turns into NP of 0 squared again, and the P of 0 multiplies that, and we have the same effect happening here. This becomes n times 1 minus P of 0 squared plus 1 minus P of 0 times 1 is 1 minus P of 0 plus P of failure and P of 0 squared plus P of failure 1 minus P of 0. Now, we're going to combine, now we're going to take advantage of the fact that 1 minus P of 0, this guy, for example, plus P of 0, that's this guy, is 1. So these two, minus P of failure times 1 minus P of 0 plus minus P of failure, P of 0 is just minus P of failure. So this guy turned into minus P of failure. And, okay, okay, here we have, here's P of 0. Here's 1 minus P of 0. The P of 0 minus P of 0 cancels, and we just have plus 1. Now, and so what we end up with is n P of 0 squared plus P of failure n P of 0 squared. And this math is really hard for this guy. It's constantly blowing out because there's just too much math. It's really angry at me about this. Okay, I think you guys might be angry with me about this too. Probably. But anyway, we'll keep on going on this. This arithmetic will appear in your class notes once I upload your class notes again. Okay, so like I said, we're just taking this 1 minus P of 0 and canceling out the P of 0s, and this came to n minus np of 0 plus this p of 0 cancels out. It becomes p of failure np of 0 squared minus p of failure plus n 1 minus p of 0 squared plus 1, that's this 1, plus p of failure of 1 minus p of 0 squared. And now we'll factor out the p of 0 squared and the 1 minus p of 0 squared. Okay, there's 1 plus p of failure times np of 0 squared is 1 plus p of failure times n times 1 minus p of 0 squared. So this factors out to this rather simple formula, and then what's left after I factor that stuff out is this minus p of failure plus 1. So we end up with this formula. And that's about as simple as I can get it. So what happens is we take, yes, I am sorry, computer, you can do it. Okay, so we take this guy. This is the formula we end up with. A little bit complicated, but it's not too bad. Okay, so if this was 1/2, and this was 1/2, this would turn into 1/4 plus 1/4, which equals 1/2. So this would be 1/2 of 1 plus p of failure n minus p of failure plus 1. Okay, over 2. Now this is basically, okay, so if p, now remember p of failure goes from 0 to 1. P of failure is 1, this becomes 1/2 of n of n. That is, if you're always searching for stuff that's not in your hash table, it's going to take n over 2. Now, if you always were searching a list for what's not in the list, it would be n. So the hash table would be half if it was a perfect hash. If it's not, this is how to tell. You square all the items. And in fact, you can use exactly the same algebra. It's just a little more mathy to come up with this formula for any hash table. So we're going to say a hash table has hash value I. So if we have 3 items, I will go from 0 to 2. If we have 10 items, I will go from 0 to 9. And we're going to give each of these, and hashing to each of those items, probability of pi. So if it was a perfect hash, this would be 1 over the size of the table, and the sum would, and regardless, the sum equals 1, because you're going to hash to something. Okay. Otherwise, your program has a bug. If you have, we'll assume your hashing program is correct, and it doesn't have a bug, and every key hashes to something. So it's the same math to get this formula, 1 plus p of failure, n, the sum of pi squared minus p of failure plus 1. So once again, if you never fail, if p of failure is 0, this is n, okay, times the sum of pi squared plus 1 over 2. This, you remember, n plus 1 over 2 is the probability if you're successful of searching. If p of failure is 1, it's the sum of np, the sum of pi squared. Now the difference is, if it's a perfect hash with sum of pi squared, where if it's a uniform distribution, a perfect hash, then the sum of pi squared is 1 over s, where s is the size of the hash table. So the hash table perfectly divides out, makes it, so a hash table of size s makes your search 1 over s times faster. If you make your hash table proportionate to the size of the data, then that makes it O of 1. Now, if your hash is imperfect, well, okay, the worst case is if it always hashes to the same item. Then the sum of p, then one of the pi's is 1 and everything else is 0, and the sum of pi squared is 1. Then this code reduces to, this guy turns into 1, and you will see that this code ends up with the same, it looks a little different, but it's actually the exact same formula we worked out for searching a list. Now, if the sum of pi squared, and so that tells us, now usually the sum of pi squared is not perfect, it's not perfectly uniform, it's not 1 over s, but it's usually fairly good. It's fairly near. So let's run through an example. So let's say we have a 3-item hash table, and instead of having 1/3, 1/3, we have 0.5 squared, and the other two are 1/4. Now, a perfect hash would give us 1/3. But if it's 1/2 and 1/4 and 1/4 squared, it gives us a little more than 1/3. But a lot like 1/3, 0.375. So we're off by about 0.42 or so, 0.042. Not a huge difference. You have to be really bad, okay? Let's say there were 5 items in the hash table. So, and let's make it really biased. We're going to make 80% of the time. It's the first item. And then the rest of the items are uniformly distributed. So that gives us since that's 2%, 0.05% of the time. Now this one should be much worse, okay? Because we're really moving 80% of the stuff into the hash table. I should rarely write this in a spreadsheet. But that's right. And indeed, instead of getting 1/5, I have 0.65. So if you have a really biased function, it will get, but still, even with all this bias, it's still getting you some significant speed up. And of course, if you have a hash function that's hitting one of the cells 80% of the time, that is a really bad hashing function. Okay? Even if it's not, right? That's a really non-uniform distribution. Typically, the kinds of non-uniformities you get from, say, the fact that your data is not uniformly distributed. So, if you're hashing words, not all combinations of letter are equally probable, will be much more like this case than like this case. And in those cases, you won't, oh yes, my game is played, yay, who cares? You guys realize I am home here. And so this gives you some idea of what's going on. So I'm going to stop here and talk about a new topic next. But I hope you guys can get what's going on here. The algebra looks complicated, but it's actually not really very bad as compared to real-world problems.